Hello and welcome to this quick take video focusing on how to verify your Vivado HLS design. In this quick take video, we'll provide an overview of the verification flow for both C and RTL designs. We'll explain the importance of validating the C, explaining the concept and good attributes of a good C test bench. We'll then demonstrate how to validate a C design, including how to invoke and use the Vivado HLS C debug environment. And finally, we'll show how easily we can verify the RTL design when using Vivado HLS. This diagram shows an overview of the Vivado HLS verification flow. There are two main steps in this flow: validate the C and verify the RTL. C validation is used to confirm the functionality of the C code is correct, that the C function for synthesis is performing the correct operations. RTL verification confirms the RTL functionality matches that of the C algorithm. Notice the RTL verification reuses the C test bench. There is no requirement to create an RTL test bench when using Vivado HLS. Before we proceed, it's worth spending a few moments to discuss the importance of the T test bench and to explain what we mean by the C test bench. The main function is at the top level of any C code. The main function cannot be synthesized. Top level for synthesis is any sub-function below main. The test bench is any code not below the top level function for synthesis. The following diagram helps explain this concept. Function main is at the top level of the C source code. Within the hierarchy, function sub-func3 is identified as the top level for synthesis. Everything below this function will be synthesized. This is referred to as the design function, or sometimes simply the top level function. Everything outside this area is referred to as the C test bench. All code which is not below the top level function for synthesis is part of the test bench. It helps test the design function. Now, let's discuss the importance of a self-checking test bench. An ideal C test bench should check the results and return a value of 0 to the function main if the results are correct. First, we'll explain this and then explain why it's such a good idea. The following code shows variable ret being set to a value of 1 at the start of the test bench. In this example, after everything has been computed, the results are saved to an output file called output.dat. This file is then compared with the expected result. If it returns the value 0, the results are the same. Optionally, some code could be used here to print the results of the comparison. The important point is that the results are checked and the function return is set to a value 0 if the results are correct. Vivado HLS can then use this return value in the RTL verification. If the test bench checks the results, as we shall soon see, verifying the RTL is simply a push button operation. Now let's demonstrate this verification flow from top to bottom. Vivado HLS invokes showing the welcome screen. For this example, we'll start by creating a project from the examples. All of the examples provided with Vivado HLS are provided with a self-checking test bench. Clicking on the Browse Examples link opens a list of the example designs which accompany Vivado HLS. We'll select an example, and selecting Next provides with options on where to save the project. Once we select the path, selecting Finish will open this example project. The first thing we'll do is examine the test bench. If we scroll down, we can see the output from the function is written to a file, results.dat, and that this file is compared with some golden results. A return value of 0 indicates the results are the same as the expected results. Since the file results.golden.dat is called by the test bench, it must be included in the test bench when setting up the project. This can be done in the project wizard, and we can see a similar screen as the project setup wizard by examining the project settings and selecting simulation. Alternatively, we can see how this is done in Tcl by examining the script.tcl file created for the project. Here we can see how both the test bench and the data file are added to the project. The next thing we'll do here is compile the C source code. And we can perform this using the Build button on the toolbar. After this completes, we can now run the design. In this example, we'll run in the C debugger. During this process, a window will open asking us if we wish to switch perspectives. Notice in the upper left-hand corner, there is a list of different perspectives. Since we wish to use the debugger, we'll select yes, and this will automatically switch us to the debug perspective. The best way to explain the debugger is to start using it. The first thing we'll do is start to step through the code line by line. Here we must first fill up the array with input data, and then we'll step into the design function. If we expand the window to view the code, we can see that in this simple example, we're simply accumulating the input. By clicking in the margin, we can set a breakpoint. Using the resume button, we can jump to the next iteration of this loop, stopping at the breakpoint. Notice the variables will update each time we iterate through the loop. We can repeat this until the function finishes. If we expand the console window, we can see the function passed. We can also run the C simulation without the debugger using the Run button. This can also be performed from the synthesis perspective. If we select the Run button, C simulation proceeds. Once again, the console window shows the C simulation passed. Before we demonstrate the RTL verification flow, we must first synthesize the design. Now that synthesis is completed, we can begin RTL co-simulation. Co-simulation because it uses the C test bench and the RTL design files. The co-simulation toolbar button can be used to open the co-simulation dialog box. Here we can select System C, Verilog or VHDL results to be used for RTL simulation. If Verilog or VHDL are selected, the HDL drop-down menu allows the HDL simulator to be selected. For Windows, only ModelSim is supported. ModelSim VCS and Riviera are supported on Linux systems. If an HDL simulator is used, the path to the simulator executable must be specified in the system search path. For now, we'll use System C RTL. This has the advantage that no HDL simulator license is required. This means RTL verification is always available from within Vivado HLS. In this example, we will select the dump trace option. This will result in a BCD file being generated for each function in the design. Pressing OK starts simulation. During this process, the C test bench is executed to generate input stimuli for the RTL design. The RTL design is then executed. And finally, the C test bench is executed again, with the RTL results being used in the C test bench for the error checking. The console window shows the verification passed, and the verification report opens in the information pane. If the self-checking test bench had detected different results from the expected results, a fail message would be shown. Once simulation has been executed, a sim folder will appear in the solution folder. Many of the files in here are work files used to run the simulation. However, if we navigate into the System C directory, since it was the System C RTL we chose to simulate with, we can see that a VCD file was produced. This can be opened with any analysis tool which supports VCD format, and the waveforms from the RTL simulation can be analysed. If Verilog or VHDL is used, then a Verilog or VHDL folder would be created and any VCD files would appear in those directories. The key message to take from this demonstration should be the importance of a self-checking C test bench. This allows both the C and RTL verification steps to be as we have seen, a push button process when using Vivado HLS. This completes this quick take video on verifying your Vivado HLS design, and thank you for your time.